Good morning, everyone. My name is Cesario Tavares. I'm a postdoc at Texas A&M. And today I want to talk about a method that we're using to focus on incorporating new materials into existing concrete formulations in a fast way. And that's why this title is From Data-Driven Models to Material Characterization to develop and improve durability and mechanical performance of higher strength concretes. So the main topic that we try to address as a whole, as an industry right now, is the decarbonization of the concrete industry. And as you all are familiar with the different efforts that are being made right now, we have readily implementable strategies from here until 2050, where we have the goal of reaching carbon neutrality. And we have other promising solutions that will get us along the way. And our research group has been focused more, have been focusing more on the efficiency of concrete proportioning and also connecting that to the efficiency of structural design. I will talk more about the structural design part in the UHPC session. And how we look at the effects of these concrete mixtures directly into structural elements. But I'll focus right now more on the mixed design efforts. So, like I said earlier, the motivation, it's related to the fact that green materials surge every day. Green cements, waste materials, everything that can reduce the carbon footprint of concretes. And you have different examples that surge every day, but the issue is we don't have all the data out there to use AI model to optimize mixtures with these cements that fast, especially the ones that don't use or don't have the same composition as traditional concretes. So these typically lead to extensive studies to assess all the performance needs, the unknown long-term performance of these materials in concrete, and the limited data available for complex AI modeling. So there's a major need for efficient tools to expedite the incorporation of these materials into new and existing concrete formulations. So we want, in a short period of time, know, okay, how much of each ingredient we need for a certain application for these materials to be ready to go, at least not to take 10, 20 years of research so we can get there. So the key is on having mixed design tools that efficiently get there, and also have tools that allow us to evaluate the trade-offs between performance, cost, and emissions, all simultaneously in an easy way to follow. So the first research question to get us there, so can we effectively optimize concrete mixture design with few experimental runs? And the answer is, it depends on the performance that you're looking at and the purpose of your optimization. So in our case, like I said, we want to get to levels of performance that will get us closer to what we expect from that material. So we design our experiments with a factorial design database matrix. In our case, we use orthogonal arrays. We use machine learning models that are supervised and that are easy to operate in low volume data sets. We compile this matrix of predictions for the different models for each performance, and then we develop what we call multi-objective density diagrams, which can filter out mixtures that don't perform for a certain threshold for what you expect. So this is an example of an orthogonal array that we used in a previous study, where you see we can collect strategic data points in the domain to model and estimate the behavior, not necessarily predict to the highest accuracy, but you can at least understand what's going on in that domain. This particular study, we used two algorithms, KNN and random forest. We used an ensemble technique that will allow us to use, to join these two models to improve prediction in the domain. And we have two case studies that are going to give us an example of how this optimization strategy would occur. So for instance, we're developing a binder for a 3D printing application. Main goal, high early strengths, low shrinkage, and to have high pumpability. And we're also looking into a mix that's self-consolidating, that's also high early strengths with low shrinkage. We measured a number of fresh and hardened properties just for the concept, proof of concept. We looked at compressive strengths at different times. We looked at the static flow, which is basically just the self-consolidating, dynamic flow when we're adding the energy, so we can see if the mix is thixotropic, so it's not moving when we remove the cone, but then we add energy, it's spreading. And we look at setting times and free shrinkage. The variables for this study is a calcium aluminate-based mineral admixture. It's not a calcium aluminate cement. It has some more components to it. We're still writing on this paper, so we won't talk that much about it, but we looked at superplasticizer content as well and low water cement ratios. And when we estimated the compressive strength with this data set, as you can see, we are able to have a good correlation between prediction and experimental measurements, both in the training and testing set. And that's typically what we expect from an AI model, to avoid overtraining, over-smoothing, and also data leakage. As you can see, the model is not perfect because the data set is very small. In fact, this data set was built with 36 mixtures only. But we can understand for different times how it works. But again, this method doesn't work for all the properties. So you need to understand which performance levels you're looking at and what works or not. So as expected for the flow, that's not enough information. The variables that we use will not estimate the behavior, especially once you pass the saturation point, then the flow of the mix will always go off the table. So it's very hard to predict that. But one of the works that we are focusing on now, and we're working with some folks from the Argonne National Lab, is to use these methodologies. So we establish the data set with the design of experiments with orthogonal arrays. We model initially, but then we use a new AI algorithm that some researchers there developed that they call target adaptive design, which is a model that models uncertainty, and it basically will guide the new batch of experiments, and then you keep feeding the model until you get the accuracy that you need. So this will tell you basically how many numbers of tests you need. It depends on the performance that you're looking at. So if you want to look more into this method, we published a paper last year on this data collection. But now, to answer the second question, can we evaluate mechanical performance as a function of the changes in mixed proportion in an easy and intuitive way, without having to just rely on the black box nature of the AI model and the accuracy parameters that we typically deal with, residual mean squared error, the standard deviation, and all of that. So the performance density diagram is basically just a diagram resembling a matrix of counterplots, where your variables are in the x and y axis, the most important variables, and the ones that have a least impact in your response, you can place them as in blocks in your diagram, and the outcome is the density of the diagram. So to give an example for the self-consolidating application, so we started with a diagram where we are plotting the setting time, the initial setting time. And you can see for different levels of replacement for these mineral admixture, different water cement ratios, and different superplasticizer contents, we can see what we expect from the model. And now, to combine all of these predictions for the different outputs, so strength, flow, and setting times, we can start filtering out this diagram. So for instance, we started by filtering any mix that sets after an hour. Then we filter out any mix that has a self-consolidating flow outside of this range between 22 and 34 centimeters. And this is higher than what we typically have in self-consolidating concretes because, like I said, we are optimizing the binder now. So we are giving some room to incorporate aggregates later and not have to increase the superplasticizer content a lot. We filter for strengths, different levels of strengths at different hours. And finally, once we have, as you see, it starts getting smaller and smaller because now you have less mixtures that will give you this type of performance. We identified two mixes in that range, one with a very high risk of cracking and one with low, because we wanted to see how the shrinkage model was also working because the predictions were not that great, but we wanted to still make sure that we can track mixes with very high probability of cracking. And this is an example of the restraints we put in the 3D printing mixes, which obviously is different. This one we want high early settings, but like I said, we want a dynamic and static flow that are different, and we want high early strengths. And at the very end, what we did is we picked these mixtures that the model predicted as optimum. We plotted against the thresholds that we said we wanted to see. And as you can see from this figure, the mixtures did follow the trends that we established, that we expected. So we wanted high early strengths, but we wanted to make sure that this mineral admixture was not staggering the strength development from the cement. We want to make sure that if you're forming these ettringite crystals, they are small enough that they will still give space for CSH growth. And this is basically what we tracked for the 3D printing mix, and the same for the self-consolidating ones. Now the next stage of our study will be to take these mixtures and get to the material characterization phase. We started the XRDs on the dry powders. We are going to make XRDs evaluations on the fresh pastes as a function of time, because we want to make sure that we validate what we expected in our initial design. What are the size of our ettringite crystals? Are they what we expected? What type of phases are we forming? Are we even forming the same phases as we do with typical concretes? So instead of looking at material characterizations and then modeling with machine learning, we'll basically doing the opposite. We're finding, optimizing mixtures, and then looking at their microstructures and see if there's anything new. And regarding the performance density diagrams, we also have a publication that we did last year where the focus was on UHPC in this case. And in this study, just to give you an idea, with 75 data points, we developed a UHPC mix with 155 megapascals, with a high fine aggregate content, and with a very low cement content compared to what we found in the literature. And all of this optimization was done with 75 data points in general. So again, just to answer a general question that we always think about how many points we need, it really depends on the property you're trying to optimize, the application. To give you another example, we need to look a lot at the different other areas. I have a colleague who just defended in computer science, and his thesis is on cuffless blood pressure measurements, and he literally uses 10% of the training data and 90% on the testing data, but that's because his model is a physics-informed model. So he's combining constitutive equations from blood pressure with AI models to predict what is your, to measure and predict blood pressure. So it's a very interesting approach. I think there's a lot of that we can apply to our case, especially To give you an example, creep measurements. It takes years and years. Even if you want to use temperature superposition methods, you still need to get 4 or 5 years of measurements to get anything that's reasonable. So if we start developing these viscoelastic intelligent models, where you're combining the constitutive equations from viscoelasticity with AI models, we might get there with very little experiments. So, yes, I got that. So the conclusions for the second question is, can we look at it in an easy and intuitive way? I believe we can if we can look at inside our models and not only at the accuracy parameters. We want to see if the models make sense, if the trends inside our models make sense or not. Yeah, and then I have the related publications here. If you don't have time to get them, I can always, you can reach out to me. I'll give it to you after the presentation. And the more complete publication you can find is on my thesis. There's, the whole approach is there. But yeah, I want to acknowledge the research team. The projector is not making a great job, but just want to thank our research team in Texas A&M, and I want to thank you for your time, and let me know if you have any questions.
I'm Jed Diab again from the University of Texas at Austin. I wanted to ask, what are the procedures you follow to prevent data bleeding in your algorithm?
Data leakage?
Yeah.
Yes, thank you. That's a great question. I'm always worried about passing the presentation time, so a lot of details are left off, but...
I appreciate it. And could you also mention what data leakage means?
Yes, so for those who are not familiar with machine learning or AI in general, let me go back really quick. Okay, so the main problems we typically look at, like I said, is overtraining, oversmoothing, or data leakage. So overtraining is when you have a high prediction accuracy in the training set, but a low performance in the testing set. Oversmoothing is when the prediction performance is bad in both sets because you use very large number of the tuning parameter. And data leakage is when you have high accuracy in the training set and testing set as well, but that's because information from one set leaked into the other. So, and that can be both ways. So you'll have very high accuracy in one, and in the other end, you'll think your model is good because the accuracy is balanced. So, and that brings to the great point that Zhenzhao told later. So you got to be very careful with those 96, 95% accuracy models, because that's typically a sign of data leakage, in my opinion, especially when in the field we measure standard errors of, like I said, 500 PSIs, but then you see models that will tell you that the accuracy is, the prediction accuracy is 200 PSI or 100 PSI. And I always ask, how is your model more accurate than what we get in the field or what the data you use to feed it? So we got to be very careful with that, in my opinion, so people don't think that machine learning doesn't have that much application in our field. If that answers your question. Thank you.
Hi, it's Emilia from Leeds again. Can I ask, why did you choose to use KNN instead of, for example, multiple linear regression after the design of experiments, the orthogonal arrays approach?
That's a great question. So my PhD dissertation started with fibers and UHPC, and I decided to adventure in machine learning in my third year. So I tried to learn the fundamentals as much as possible, like oversmoothing, overtraining, and that, rather than looking at learning a lot of different models and a lot of different softwares. So I kept my expertise on KNN and random forests. I tried to limit to that, but I'm now trying to look into more other different models like AdaBoost and complex models also like ANN. But simple, quick answer to your question, those are the ones I learned at that time.
Yeah, okay, brilliant. Thank you.
Thank you.
Yes, last question.
So I'm Karthik Obla, I'm with an NRMCA. It's not a question that on this presentation, but a general comment about AI models in general that I had is that maybe an issue for the committee perhaps to look at, right? So we have data residing in different places, right? The cement producers, the SC, ingredient, fly ash, all those, they have their own data. The concrete producers, they have their own data. And then the testing labs, they have their own data, right? So, and many times the data is not shared, right, all around. And the testing labs may not have, provide the data to the producers and vice versa and all that kind of. So for a model to work, you need to have all the data coming together, right? And if you think about it, we test about 400 million yards a year of concrete in this country. We got about 3 million data points every year, right? So of course, that's a lot of data points to do your model. The challenge, of course, is that whether we're capturing all the variables, right? So that's the other thing. It's good to do in a lab, a few mixes and get a model, but if you like so many things, then the variability just blows up, right? There was a producer in Phoenix who would just look at all the technicians who were testing his concrete, right? And he will grade his technicians based on the testing variability. And at the end of the year, he'll give a gift to the one who gets the best, lowest testing variability. So a testing technician could also be a variable in the test strength, right? So you could have testing technicians who give you better strengths than lower strengths. So we need to think about actually incorporating all these variables into this model. Only then it's going to get more and more accurate, right? So just some thoughts.